participants, good morning. My name is Untitled. I'm a PhD student, and the subject of my today's presentation concerns the study of hydraulic line phase for cultural heritage application. We will start first with a little bit of the theoretical background of the topic, accompanied by the literature review. Then we will take a look at the experimental procedure and the results, and finally we will reach our concluding remarks. So, in the island of Chios, there is a building of the National Bank built at the beginning of the 20th century. And at these 100 years past, there have been restoration activities quite a few times. So, we have the following questions. What are the appropriate materials if we want to restore such a building? Do we apply modern materials, such as reinforced concrete? Is it maybe traditional lime paste? Or maybe we use some polymers? Or do we just leave it at its destined form? So, let's examine the first case. Cementitious-based materials have been linked to salt damages, and also there is no compatibility between the mechanical properties of the cementitious materials and the original building materials. And as you can see in the picture, cementitious materials are linked to accelerated deterioration. So our first case is overruled. Now, let's examine the second case about the application of hydraulic or non-lime mortars. So, 70 years ago, there have been extensive restoration activities took place in Machu Picchu in Peru. And after so many years, the interventions remain practically intact. So, it has been seen that lime mortars are actually the appropriate materials to conserve such buildings. So, examining a case from Greece, namely the Palace of Galerius in northern Greece, Thessaloniki, in 1971, restoration processes took place and cement mortars were applied. But again, it has been seen that accelerated deterioration took place, and so 4 years later, the same works had to be repeated. And at that time, they applied lime-based mortars, and then still the interventions remained in. So, this is what the subject my research team dealt with, and actually this project is part of a much bigger one, Akista research project, with partners from different cities of Greece. So, the targets of our research project is, first of all, to investigate the application of compatible matrices, and this is currently in progress. Secondly, we want to incorporate functional carbon-based nanomaterials aiming to develop self-sensitive mortars. And our final goal is to study the piezoresistive response of those composite materials so that we can see whether the material can act simultaneously as a sensor. Examining the logic behind our first goal, we know the following: that lime-based materials are used in restoration of cultural heritage monuments. And currently, the study of novel lime poisonal mortar is gaining scientific interest. But before examining the final mortar, we want to take a look how the binder fraction behaves, and that's why we examine lime-based paste. So, moving on with the experimental procedure, let's take a short look at the flowchart. We receive our materials and then mix them according to the ASTM standard C305. Then the mixture is cast into molds. The different batches maintain in water with calcium hydroxide either for 3, 7, or 28 days. And then we test their mechanical properties. Taking a closer look to our materials, our main material is natural hydraulic lime 5. Number 5 means that after 28 days, its compressive strength should be at least 5 megapascals. And according to the appropriate EX standard, we expect a strength from 5 to 15 megapascals. The pozzolan material we add is metakaolin at a percentage of 20%, and then we decide a different water to binder ratio. Now let's see our main experimental procedure and the setups we used. First, we start with the flow table test. This is the setup, and in case you are not familiar with it, it has a pretty simple logic. We turn the handle, the disc elevates, and then is dropped continuously for 25 times in about 15 seconds. And according to the European standard ASTM-C 1437, we expect the flow to be 105% to 115%. So, after that, we test the mechanical properties. The 4-point bending at prism with dimensions 20 times 20 times 80 millimeters, and also we test the compressive strength at cylinders with the diameter of 30 millimeters and the height of 60 millimeters. So now we will present the results for this different procedure. We started with the water to binder ratio of 0.3, and we saw that the mixture was actually very stable. And then, at the step of 0.05, we finally reached our optimal water to binder ratio, which was found to be 0.55, because it gave us a flow of 111%. Water to binder ratios higher than that actually produced a liquid. It was the fluidity was very high. And we always work at this optimal water to binder ratio. So now we'll take a look at our mechanical test results. The specimens were tested at the ages of 3 days, 7 days, and 28 days. We present the individual curves for 7 days, where the average flexural strength was found to be about 1.4 megapascals with a standard deviation of 0.07 megapascals. But let's take a look at the comparative results for 3 days, 7 days, and 28 days. Of course, the tendency shows an increase, and at 28 days, the maximum flexural strength was found to be at about 3 megapascals. So, in the same logic, we continue with our compressive test results. The average compressive strength at 7 days was about 3 megapascals with a standard deviation of 0.17 megapascals. And the comparative results. We can see that at 28 days, the average compressive strength is about 6.2 megapascal, and this is in accordance with the experimental results according to the before mentioned standard. Reaching my concluding remarks. So, the optimal water to binder ratio was found to be 0.55 in order to prepare workable mixtures. Flexural strength decreases within the acceptable range, and also compressive strength was found to be in accordance with EN 459. So, our future steps include, since I already mentioned that we are in an initial step of our research, so we want to examine further the physical and chemical properties of the paste. We want to investigate the application of different types of aggregates in order to develop the final restoration model, and then we would like to incorporate different types of carbon-based nanomaterials to the matrix. So, for this project, we would like to acknowledge our founding fathers, since our research project is co-financed by Greece and the European Union. And I would like to thank all members of my team who are here to support me, and of course to thank you very much for your attention.